Okay, let's keep going. Okay, here. Okay, let's take a look at this kernel for the posterior density of beta. Okay, let's take a look at this exponential function. What is this? What do you see from this exponential function? You see here exponential function, right? This is clear. And then in the exponent, what do you see? You see quadratic term of the random variable, and then is linear term of the random variable. Okay, so the integral, this is sort of the quadratic equation, right? Are you familiar with this? Form, right? Exponential function, and then in the exponent there is square term and linear term. What is this? What is this? This is kernel of what? This is kernel of what? This is kernel of what? Let's go back to here. Let's go back to this here. Just ignore this normalizing constant. Let's ignore this normalizing constant. Okay. Here is exponential function. And then in this exponent, what they are? You see beta prime beta, quadratic, or I say beta square term. There must be beta square term, and what? Just beta term, because here beta prime beta b0 inverse times beta 0. This is just beta term, right? Same for here. So this is normal density of y, right? Exponential within exponent y prime y, or we say the y square term, and y prime times x times beta. This is just y term, right? So then now you see that this is a kernel of normal density. So that means what? Beta given y follows a normal distribution. Okay? Now finally we figure out the kind of distribution of beta, right? So now we can see that beta follows normal distribution given y, right? But still we don't know its mean and variance, right? We know it's the class of distribution, right? We know it's class of distribution, but we don't know exactly what the mean and variance are. Okay. So then now from this point on, I'm going to explain how to figure out its mean and variance, given that beta follows a normal distribution conditioned on y. Okay, right? So to do this, here is a note here. Suppose just consider a normal density, and its mean is beta 1, and its variance is sigma square times b1. Okay. Then by definition, this is its normal density. It's multivariate normal density. Okay, and then I just arrange this equation in terms of beta square and beta terms. Okay, right? And so this is the kernel. This is kernel of the beta. Okay, right? So if the mean is beta 0, beta 1 and variance is sigma squared times b1, then this density must have this form, right? Okay, so then let's compare this equation. Let's compare this equation with what? With this one. With this one. Okay. So then you see that this term is the same. Minus 1 over 2, minus 1 over 2 times sigma squared. Okay. And here, beta prime, here is beta prime. Here is beta, and here is beta. So then B1 inverse corresponds to what? B1 inverse should be equal to what? X prime times B0 inverse. Right? This is B1 inverse. And what about B1 inverse times beta 1? Where is it? This term must be equal to what? Here, x prime y times b0 inverse times beta 0, right? Because here is minus 2 times beta prime. Here is another minus 2 times beta prime. And this term must be the same. It must be equal to beta 1, b1 inverse times beta 1, right? In short, again, so then this term should be equal to b1 inverse, and this term should be equal to this one, right? So we are matching the coefficient between these two equations, right? This is derived what? This is derived what? This is derived from the posterior density of beta. Okay, and this is from what? This is just derived from the definition of normal density, when its mean is beta 1 and variance is sigma squared times b1. But we don't know beta 1 and b1. We don't know. Just there is some number beta 1 b1, and then right here. So then what? So this term should be equal to b1 inverse. Then what about b1? What about b1? b1 must be what? Inverse of x prime x times b0 inverse, right? So that's why we have this b1, right? And what about beta 1? Beta 1 is what? We can derive beta 1 by multiplying b1 on the left hand side and right hand side. On the right hand side, this one must be cancelled out. So that's why we have b1 times x prime y times b0 inverse beta 0, right? So then what is beta 1? Beta 1 is what? Beta 1 is the mean. b1 is what? The variance covariance. Exactly speaking, the sigma squared times b1 is the variance covariance of beta. Then we are done. Right? Then we are done. Okay. Again, let me go back to here. Okay. So again, we just drive the conditional density of the beta given y using the Bayesian. Okay, using the Bayesian, and we found that this is kernel of normal density, and the question is what's its mean, and what's its variance covariance matrix, and suppose its mean and variance are beta 1 and sigma squared times b1, and according to the definition of the normal density, then it must have this form, right? So then this equation should match this equation. So then we are just matching the coefficient on beta square terms and coefficient on that beta term. Just by matching the coefficient, we could see that beta b1 must be x prime x plus b0 inverse of inverse, and beta 1 must be must be b1 times x prime y plus b0 inverse beta 0. Okay, so then finally we have the solution. We have the Bayesian estimates of the beta, or we say posterior distribution of beta, right? Beta given y follows this normal distribution. Its mean is b1 times a. A is defined as this, x prime y plus b0 inverse beta 0, and b0 is given, right? So then this b1 times a is mean, okay? And variance covariance is sigma squared times b1, okay? Okay, this is how we estimate mean and variance of beta from this Bayesian approach. And then in the next time, I'm going to explain this more intuitively and or its implications. Okay, so this is just mathematical derivation. Okay.